Welcome back. We had in the last lecture discussed the idea that by blowing up the scale of the boundary layer, we can obtain the governing equation for that layer as del u by del x plus del v by del y is equal to 0 for continuity equation, and for momentum equation rho times u del u by del x plus v del u by del y is equal to minus dp by dx plus mu del square u by del y square. Notice that we have been able to retain the viscous term for del square u by del y square, but the viscous term mu del square u by del x square is still negligible. The boundary conditions at the wall would be no slip, that is u is equal to v is equal to 0, and at the outer edge the streamwise component u tends asymptotically to a value capital Ux, that is the velocity of the outer flow at the edge of the boundary layer. Capital Ux is obtained from the Euler equation at the edge of boundary layer as rho u du by dx is equal to minus dp by dx. You notice here that the streamwise velocity component uxy tends to capital Ux, the velocity at the edge of boundary layer, asymptotically as y tends to infinity. We had obtained this solution, the Blasius solution, in terms of u by capital U as a function of eta, the self-similar variable y under the root capital U by nu x, where nu is the kinematic viscosity of the fluid. The velocity u becomes capital Ux only very far away at y tending to infinity. So how do we determine or define the boundary layer thickness? The boundary layer thickness in this case is arbitrarily defined as the distance by which the velocity in the boundary layer reaches 99% in the inviscid flow. Since the velocity u by capital U is given by f prime, so we determine the value of eta at which the value of f prime is 0.99, and that value of eta is 4.91. So we can define delta by x is equal to 4.91 divided by under root REX. In many places, this value is given as 5.0 divided by under root REX. The difference is small and is largely because of the approximation. This series of shots from the movie Fundamentals of Boundary Layer by Abernathy, that was produced in 1962 for the National Council of Fluid Mechanics films, that can be viewed at YouTube. It shows the development of boundary layer on a flat plate. The flow visualization is done in a water tunnel where hydrogen bubbles are produced by passing current through an electrode held perpendicular to the flow. Current is passed through a small interval delta t, and this white band of hydrogen bubbles are formed. These are washed down the flow, pass the flat plate, and after a little while, this is a kind of profile that you develop. This clearly shows the development of the boundary layer on a flat plate. The velocity at the plate surface is 0, and it tends to the velocity capital U far away. At a little later time, This band looks like this. This band is known as a timeline in fluid mechanics. This is at a given time, what does the flow velocity look like? At still later time, this pattern is this. This shows clearly the growth of the thickness of the boundary layer on the flat plate when that is aligned along the free stream. But as we said, the boundary layer thickness defined in the manner earlier, that is where the velocity of the flow reaches 99% of the inviscid velocity, is arbitrary. A physically more meaningful measure of boundary layer thickness is the displacement thickness, which is defined as the distance by which the external potential flow is displaced outwards as a consequence of the decrease in velocity within the boundary layer. This is the boundary layer velocity profile, and if we calculate this area, then this is the volume per unit depth of the fluid that flows past the flat plate aligned at y is equal to 0. The same flow is obtained if the flow velocity does not decrease near the plate, but everywhere the flow velocity is u, then the same flow is obtained in this distance. That means to say that because of the development of boundary layer, the flow past the flat plate decreases and decreases by an amount which is equivalent to this thickness, and this is termed as the displacement thickness, delta 1. So if we shift the boundary by distance delta 1 and we let the flow proceed with the velocity capital U everywhere, then the flow rate would be same as the actual flow rate on the actual plate with the development of boundary layer. The flow deficit that develops because of the presence of the boundary layer is this area, which is the integral of capital U minus U dy. And we equate it equal to capital U times delta 1, the displacement thickness. This gives delta 1 as an integral of 1 minus U by capital U del y, dy over the whole boundary layer from 0 to infinity. And if we use the self-similarity profile for the boundary layer discussed in the last lecture, U by capital U is the function f of eta, where eta is the self-similar variable, y divided by nu x by u. Then delta 1 is evaluated as this, where subscript 1 at the end denotes that the value of eta minus f prime eta should be evaluated far away from the boundary. If we plot f prime, which is u by capital U, and we plot f and we plot eta, then eta minus f tends to a constant value of 1.7208 as eta tends to infinity. So the value of this is 1.7208, and the displacement thickness is now given by this expression. Delta 1 by x is 1.7208 divided by under root Reynolds number. Delta 1 varies like x raised to power 1/2. This thickness is about 1/3 of the boundary layer thickness delta defined earlier as the location where u is 0.99 of capital U. Another way to interpret displacement thickness is to regard it as the distance by which the streamlines of the external flow are displaced because of the slowing down of the fluid within the boundary layer. Thus, if the flow proceeded straight, it goes like this. But now the streamlines are shifted upwards, and at this location A, capital A, this is the distance by which a streamline is shifted. This is the displacement thickness. To calculate the transverse velocity in the boundary layer on the flat plate, that is the velocity in the y direction, we determine first the stream function with eta is equal to y times under root capital U by nu x, and the streamwise velocity u equal to capital U times f prime x. The stream function is given by integration of u as psi is equal to under root nu x u times f of eta. And once we know psi, we can find out the transverse velocity by taking its gradient along the x direction. V is equal to minus del psi by del x, and this is obtained as 1/2 under root nu capital U x times eta f prime minus f. If we plot this, this is the streamwise velocity we get as a function of eta. It reaches a maximum value of 0.86 in terms of the non-dimensional variable, so that we can write V divided by capital U as 0.86 divided by under root Reynolds number. Notice that this is positive. So, the transverse velocity is upwards in the boundary layer above the plate. You also notice the transverse velocity is like 1 over under root Reynolds number. That is, it is very small compared to u. This picture shows the transverse velocity and the streamwise velocity in red, transverse velocity in blue. Both the displacement thickness, the boundary layer thickness, and the transverse velocity are shown exaggerated. But this shows that this is small compared to the value in the streamwise direction. Notice here that the edge of boundary layer is not a streamline. The streamlines of the flow enter the boundary layer as we go down the plate in the x direction, like shown here. This does not indicate that the V is negative. V is still positive. This streamline is sloped upwards, confirming that V is indeed positive. But the slope of the edge of the boundary layer is more upwards. That's why the flow is entering the edge of the boundary layer. There is entrapment of fluid within the boundary layer. There is another concept that is used routinely in boundary layer theory, and that is the concept of momentum thickness. Now, the momentum flux at A is integral across the boundary layer from 0 to infinity of rho u square dy. Here, the mass flux in a strip of thickness dy is rho u dy, and the streamwise velocity is u, so the x momentum is rho u square dy in a strip of thickness dy at y. And the total momentary flux is obtained by integrating this across the boundary layer. Now, the momentum flux, if the actual mass flow had the inviscid velocity capital U, would have been rho uv dy integrated from 0 to infinity. That is the mass flow rate rho u dy multiplied by the inviscid velocity capital U. This results in a deficit of momentum flux of rho u times capital U minus u times dy integrated. This can be accounted for if we displace the boundary, that is the plate, upwards in the inviscid flow by an amount delta t, given by delta 2 is equal to 1 by rho u square. The integral from 0 to infinity of rho u times capital U minus u dy, which can be written in this manner. Recall that u by u within the boundary layer on a flat plate, which is self-similar, is a function of eta, which is y over delta, which is a function of eta. If we express this as an integral in terms of eta, then this would be independent of x. And that's what we do next. So with y divided by delta c, the characteristic thickness in the y direction, as under root nu x by u, we get y times u divided by dx is equal to eta, as introduced by Blasius. And then u by u is f prime of eta, and we get delta 2 as under root nu x by capital U integral 0 to infinity of f prime times 1 minus f prime d eta. This clearly is independent of x. For a flat plate, the value of this is 0.664. So that we can write delta 2 by x as 0.664 divided by under root Reynolds number based on x. So delta 2 also varies like root x. In this table, we summarize some results for a flat plate boundary layer. The boundary layer thickness delta, defined as the location where 99% of the inviscid flow velocity is reached, is given by 4.91 divided by under root Reynolds number. The displacement thickness delta 1 is 1.73 divided by under root Reynolds number based on x. And notice this is about 1/3 of the boundary layer thickness. The momentum thickness is another third lower, 0.66 divided by Rex. And the skin friction coefficient, which is defined as tau W divided by 1/2 rho U square, is obtained as 0.664 divided by under root Reynolds number. The skin friction is obtained here as mu times du by dy, which was obtained in the last class as 0.664 divided by under root Reynolds number times 1/2 rho U square. Note that some authors use delta star and theta to denote the displacement thickness and momentum thickness respectively, instead of delta 1 and delta 2 used here. So do not get confused if you follow some other authors. The ratio delta 1 over delta 2 of a boundary layer is often used as a measure of the shape of the velocity profile. The value of the shape factor on a flat plate aligned to the flow, like we have been discussing so far, that is, for a blastous profile, has a value of h, the shape factor, as 1.721 divided by 0.664, that is 2.59. Since delta 2 is related to the shear stress on the wall, a high value of h, that is the ratio delta 1 over delta 2, indicates a decreased value of shear stress. It will be seen later that at the point of separation of boundary layer from the wall, the shear stress tends to vanish. Here on a wall, we have shown different boundary layers profiles. At this location, du by dy at the wall is 0. This is the point of division between the attached flow here and the separated flow here, which is indicated by the reversal of flow near the plate. And this is where the shear stress is 0, or the value of h, the shape factors, tends to become very large. And so the increase in value of h indicates that we are approaching separation. Let's relate drag to these various thicknesses that we obtain. Let us consider a steady flow on a flat plate. The boundary layer grows as shown. The streamlines are as shown. Consider a control volume starting from x is equal to 0, the leading edge of the flat plate, to the location A, and spanning a distance a little more than the boundary layer thickness at A. Outside the boundary layer, the dotted line, the velocity horizontally is equal to capital U. Inside the dotted line, the velocity varies with y. We assume constant pressure all around. There would be a flow that will leaving the upper surface of this control volume. Let the rate at which the mass leaves this upper surface of the control volume be m dot. So, the momentum it carries is m dot times capital U, the inviscid velocity, the x momentum. And what is m dot? M dot is obtained as the mass entering this left control surface and leaving at the right control surface. The mass entering the left control surface is rho u times delta prime per unit depth. U is capital U, the inviscid velocity. And the mass leaving this is obtained by integration of the velocity profile there. So, clearly by mass balance, m dot is rho u del prime minus integral from 0 to del prime of rho u dy across the boundary layer at location A. Then let us consider the momentum balance. The momentum flux at the top, and it is in a flux, is that m dot times capital U, and with the expression m dot obtained, this is given by rho u square del prime minus integral from 0 to del prime of rho u capital U dy. This is the momentum flux at the top surface. And the momentum influx at the left surface is rho u square delta prime, because everywhere the velocity is the inviscid velocity capital U. At the right surface, the momentum flux is obtained by integration of rho v square dy. And so, by momentum equation, we get the net efflux of momentum must be the net horizontal force applied on the control volume towards the right. If the drag force on this surface is d prime per unit depth, then this force is minus d prime, because the drag is applied to the left. We consider forces to the right as positive, so we use minus d prime. Simplifying, we get d prime is equal to rho u square delta 0 to 1 u by capital U into 1 minus u by capital U dy by delta. You notice this is like momentum thickness. Momentum thickness delta 2 was defined as this, so that we can write d prime, the drag per unit depth of the flow, as rho u square L times delta 2, where L is the length up to the location where your control volume ends. And the drag coefficient CD is this drag divided by 1/2 rho u square times the area of the plate. For unit depth, the area is just the length of the plate L. And so the drag coefficient is twice the displacement thickness at the location x is equal to L. a very important result. That is the importance of momentum thickness. The deficit created in the momentum flow because of the velocity profile in the boundary layer. Now let's express this in terms of shear stress on the wall. This is d prime that we obtained. D prime is the drag per unit depth and can be expressed as the integral of the shear stress tau w. D prime is 0 to x tau w dx, with x is equal to L, or by differentiating we get tau w, the shear stress at the wall, as d of d prime dx. And since d prime is now in terms of the momentum thickness, the shear stress is obtained as the derivative of the momentum thickness. Thus, we obtain Cf as twice the derivative of momentum thickness with respect to x. This result, which will be used shortly to obtain interesting results by a much easier method than was used by Blasius.